Welcome back to the channel. In today's video, we're going to look at coffee, but to do so, we're going to take advantage of the fact that we can collect our own near-infrared spectroscopy data on these sorts of material. And the idea is now to compare an unknown coffee sample to 4 other known materials. And through the process of using signal processing and our understanding of the chemical data to try to determine then if the unknown material is most like one of these other materials. And in this case, I want to also highlight that the data is available. If we go to the GitHub page, I have the data uploaded as coffee NIR spectra. And if you click this raw button here, raw here, you can see that we have a web page which stores the CSV data. And we can take advantage of that in our notebook by using that URL and the pd.read CSV function to access the data, set the index column to 0, transpose it, and we can get our raw data just like this, where again, we have our 4 known materials, A, B, C, and D, and our unknown coffee. This is part of the larger near-infrared spectroscopy in the home study, but I want to pull out useful nuggets and show how we can leverage our understanding of signal processing to enhance our chemical analysis. So let's begin. So the idea in the study is to now use the Pearson correlation, which we can use as our data frame method, to determine which of these materials our sample is the most similar to. And if we just run the .core method, we will get this correlation matrix, but we can specify just the unknown column to see how similar the unknown material is to the other materials. Now, in this case, we can see that these only really differ in the 4th decimal place. And in the real world, this is a really tough call to make. And if you look at the raw data, you can see that these all look really similar to each other, where the green, orange, and purple, A, B, and C, all look very similar and slightly elevated. And the D and unknown look quite similar to each other. However, the biggest difference between those two groups is really the scattering that's present in the spectroscopic technique, which is a known artifact and can be corrected. And so given that the data is showing that it's highly correlated, it's hard to break out, and then we have these scattering techniques, this is a good case for using signal processing to enhance our interpretability of this data to determine which of the samples the unknown is most similar to. So let's create a new variable called process X, and let's get ready to chain some methods together. So let's transpose this data for processing, and we're going to pipe a method called apply SNV. And this comes from the apply SNV data frame method I've developed here, which allows us to correct for the scattering within the data by setting the mean effectively equal to 0. And so with this, we can remove a lot of this interference. And so let me show what this will do to the data frame. If we look at this and transpose and plot, we will get the data with the scattering reduced. However, this does not do much for improving the correlation of our data. So let me look at the unknown column again, and you can see that this does not do anything to enhance the correlation. And so let's add another method to this called pipe, and let's use the apply Savitzky-Golay method. And so this is another way to help baseline correct and smooth the data. And so we are going to pass in a window length of 3 and a polynomial order of 1. And again, those are the positional inputs from the apply Savitzky-Golay function, where the first position is the implicit data frame, which is covered by the pipe method. And then the window length and polynomial order are the other positional arguments. When we look at this and we look at the impact of the data frame, let's transpose and plot. You see that it doesn't do much visually to the data. If we compare now and look at the impact on the processing, it only slightly modifies the correlation coefficients of the material. So again, it's really difficult to make any sort of call on the unknown versus A, B, C, and D. However, I made a slight modification to the apply Savitzky-Golay method that I think will be quite beneficial. And that is I use this keyword args optional parameter here. And what this allows us to do is to pass in keywords into the apply Savitzky-Golay function, and that will be passed into the Savitzky-Golay filter from the SciPy signal library. And so those keywords exist, and there are several keywords. So window length and polynomial order are handled by positional arguments in the apply the self-call method, but we can take in keywords such as deriv, delta, axis, and a few others to change the output of this filter. So let's compute the first derivative of this data, but first let me set deriv equal to 0 so you can see that this is the default option. When we look at the first derivative, we will see a substantial change in the overall presentation of the data, where instead of looking at only the descattered data, we're able to see how the signal is changing, and this does make those small changes very substantial in this view. So now we can see that the traces that were quite correlated will presumably be very different by those same assessments. And so again, let's look at the process X data frame and compute those correlation coefficients. And by doing so, we can see that the unknown material and material D are in fact perfectly correlated. Material C is strongly correlated, and materials A and B are quite distinct from the rest of the samples. And so with this, we can have much greater confidence in our assessment of the unknown being highly correlated to D, and can quickly rule out A and B as likely suspects for the identification of the unknown material. And so this is how we can leverage our understanding of the measurement science and data science to improve our confidence of the assessment. And if you want to replicate this or even dig deeper, the data can be found at this link here. And if you enjoyed the video, like, comment, subscribe, and I'll see you in the next one. Peace.